In this video, I introduce Monte Carlo gradient estimation in machine learning. Computing the gradient of expectation of a function, namely a stochastic gradient, is a fundamental problem in machine learning. The objective function f is defined as here, which is not known in closed form. A function f of an input variable x with structural parameters phi is evaluated on average with respect to input distribution p with distributed parameters set as shown here. The goal is to learn the parameters set by computing the gradient eta of the expectation with respect to the distributed parameters set as shown here. If the expectation EP is not in closed form, the integral over x is high dimensional, and the cost function f may not be differential. Monte Carlo gradient estimation can be applied to solve these challenges. To numerically evaluate the integral f, the independent samples x1 to xn are drawn from the distribution P. And then the average Fn of the function f is evaluated at n samples as shown here. The Monte Carlo estimator of the objective f is defined as here, where xn sampled from Px set. The quantity Fn is a random variable, since it depends on a set of random variates from x1 to xn. A Monte Carlo estimator has the following properties. First, consistency. As n increases, Fn converges to the true value E P as shown here. Unbiasedness. If repeating the estimation process many times, the estimate is centered on the actual value of the integral EP on average. Minimum variance. Because Fn is a random variable, the unbiased estimators using same number of samples n have a lower variance. Stochastic optimization consists of two phases, namely simulation phase and optimization phase. The system is stochastic because the input parameters set influence the system in a probabilistic manner. For a regular optimization system, the output is fully predictable for a given input as shown here. Namely, the system is deterministic. However, the stochastic optimization makes a call for value estimate of a function f and value estimate of a gradient as shown here. Both the function and the gradient values are random variables. For gradient-based optimization methods, for example, stochastic gradient descent, if the estimates are unbiased, the result convergence is guaranteed. If the optimization phase is also performed with a stochastic approximation, the system is a doubly stochastic optimization as shown here in two phases, this simulation phase and this optimization phase. There are two sources of stochasticity. The first source arises in the simulation phase from the Monte Carlo estimators of the gradient, which are random variables because of the repeated sampling from the measure P. The second source arises in the optimization phase from the stochastic approximation, which introduce randomness from the subsampling of data points when computing the gradient. For more details, please check with these references. Thank you. Bye.